Hi, so welcome back to the 7th lecture of MA 221. So today we will be mainly discussing about numerical integration. But before starting that, uh, I think I should solve one of the problems in homework 2 because one of you just asked me some doubts. So I'll solve one to make things more clearer. So in homework 2, problem 4a, you need to use partial fraction to integrate this function. Okay. So the main doubt was, is this can be written as something like this? Two factors of uh, linear polynomial in X. Okay. So my denominator is this, right? X squared plus, minus 5x plus 6. So one way should be to find root of this equation, say equal to 0. Find root or roots. So you might remember, if you have a quadratic equation as ax squared plus bx plus c to be 0, then the formula for roots are minus b plus or minus square root of b squared minus 4ac over 2a. Okay, so if you compare this equation, this general equation, and this particular equation, then you can say that in this case, let me just use slightly. In this case, your a is 1, b is -5, and c is 6. So if I use the formula, then I should have something like this as my expression. Okay, cool. What is this? This is 5 plus or minus square root of minus 5 square is 25 minus 24 over 2, which is 5 plus or minus square root 1 over 2. Square root 1 is just 1, so therefore 5 plus 1 over 2, 1 root. Other root is 5 minus 1 over 2. So this will be 6 over 2, so 3 or 2. So therefore, what I can say that x squared minus 5x plus 6 can also be written as x minus 3, x minus 2. Okay, so this is my two linear factors. And then, therefore, I need to decompose this 1 over. So the original function was x squared minus 5x plus 6. We saw that that is nothing but product of two linear polynomial. And then how to decompose this? If you go back to the rule of decomposition for partial fractions, you should write that as like this. Okay, where you need to solve for a and b. Okay, so if I simplify, then 1 over x minus 3 times x minus 2 on the left is same as a times x minus 2 plus b times x minus 3 over x minus 3, x minus 2. Okay, this thing on the bottom cancels from left and right. Then you'll get 1 is same as ax minus 2a plus bx minus 3b. Collect all the terms having x. So this will be a plus b minus 2a minus 3b will be the constant. And left side you have 1. So if you compare left side and right side, on left side there is no component of x. So therefore a plus b must be equal to 0. And the constant on the right side is 2a minus 3b. And that should better be equal to 1 because that's the constant on the left-hand side. From this, I can write a is minus b, and I can use this in the second equation to solve it. So this is minus b minus 3b is 1. Okay. So I have 2b minus 3b to be 1, which is nothing but minus b to be 1, which is same as b is negative 1. And if b is negative 1, using this relation, I can say that a is just positive 1. Cool. So therefore, again, coming back to my integration, dx over x squared minus 5x plus 6 is nothing but dx over, so remember it should be like this. Write it in steps. That was same as x minus 3 times x minus 2, like that. And then that was same as a over x minus 3 dx plus b over x minus 2 dx. A was 1, so this is just 1 over x minus 3 dx. And b is minus 1, so this is minus 1 over x minus 2 dx. And then you can use u substitution or just do it directly. It's up to you. You will get ln x minus 3 minus, this minus will come out, and then ln x minus 2 plus c as your final answer. Okay. Yeah, I hope I hope that the things are better. You'll be able to solve the rest of the problems of partial fractions. Okay, now let's move to the discussion about numerical integration. So the concept of numerical integration is, suppose, let me just make a title. Integration. Okay. Suppose you have a function which is like this. This is fx. And then you need to integrate that function from point A to point B. So basically, you need to evaluate what is this. So if you consider geometry, this quantity should be same as the area of this shaded region. Okay, maybe I just different. But this shaded region. Okay, cool. So, but how you are approaching to solve this problem is you are trying to find a function capital F such that the derivative of capital F is same as your original function fx. And then you can just take integration both sides like this. And then we know that integration and derivative are sort of reverse processes up to some assumptions. Then this will be just fb minus fa, right? Basically, before that line, I should write like this. It should be fx from a to b, therefore fb minus fa. Okay. So basically, our main task to solve any kind of integration is to find this function capital F. Okay. Okay. So far, so good. But what if my integrations are quite complicated? What if we can't find an antiderivative? For example, if you have something like, I don't know, e to the minus x squared dx, say from 5 to 10, something like this. Or you have square root of 1 plus x to the third dx. So for this sort of integrations, doing by finding the antiderivative is kind of difficult. We don't have like a closed formula or something or any way to deal with it. So what we do rather is we approximate. When you cannot tell exactly what the value of the integration will be for the definite integration, say, then you try to approximate. And then later we'll see there is a question of how much error in that approximation. But let me now try to recall some things for you. So recall that when you learn the integration for the first time, maybe in Calc 1, then you studied Riemann sum. What is that? That is basically, suppose you have a function like this. This is say fx. And then you are asked to do the integration from point A to from point A to B. So this is A, this is B. Okay. So Riemann sum said that you need to divide the interval AB into n equal pieces, and that should be of length delta x, where delta x is b minus a or n. So this whole length was b minus a, and then you just divided it into n equal intervals of like same each of the subintervals should be like same length, and you name this as x naught, the first point, x1, and so on till this is xn minus 1, and maybe the last point is xn, something like this. And write it down. So a is x naught, then x1 is bigger than that, and so on up to xn, which is b. Okay. And to approximate this area, what you did is you kind of take n to be infinity, and by that you make the integration of fx dx more rigorous. So let's not go to there, I guess. That's a different topic altogether, to justify how the Riemann sum kind of indicates the integration. But rather what I want to do is to define what is right endpoint approximation. So say Rn is the notation for right endpoint approximation. What is this? This basically evaluates okay, this is evaluated at the right endpoints. Okay, to make things more clearer, so this is my function fx, this is my axis, and this is my lower and upper limit, like that. So Rn basically tries to approximate on the, and then what I do is this is my x naught, so this is my x1, and so on, this is my xn, right? Exactly like this. And delta x is b minus a over n. So, and this Rn represents that I am subdividing the interval a to b into n equal parts. So the right endpoint approximation is like this. Rn is like delta x f of x1 plus so on, like f of x2, so on up to f of xn. Why the name right endpoints? Because if you see, first my interval was a to b, and then I subdivided that into a to x1, and then x1 to x2, and so on till xn minus 1 to xn. Okay. And therefore, all of this point, if you look at this, there are endpoints, right? So I'll consider the first interval, and I'll consider the very far right point of the interval, which is x1, and I'll take the value of f at the point x1. For the second interval, the same thing. For the last interval, I'll take the rightmost point and evaluate the function f at that point, and we'll take the sum. So I'm subdividing it into n smaller equal intervals, and then I'm considering all the right endpoints. So that's why the right endpoint approximation is the name for this type of approach. Okay, cool. Okay, cool. So this is the formula basically. And similarly, we can define left endpoint approximation. So kind of same picture, but then my ln should be left endpoint approximation. And then the formula for ln should be delta x. Now I should consider all of the left endpoints of each of the subintervals. So it should be f of a plus f of x1 plus so on up to f of xn minus 1, like this. Okay, cool. And if you want to visualize the picture, then say this is left endpoint approximation. This is your function fx. You are interested in doing integration from a to b. You are subdividing it into n equal parts like this. So remember, your main goal is to get this area, right? So when you consider a to x1, x1 to x2, and so on, when you do left endpoint, then this is the height, right? So basically you are approximating this with this sort of rectangle, and you are taking the sum. So therefore, if you add all of this, you will get this area, basically. The area of this small rectangle plus area of the next one plus so on. So therefore, the errors should be this small triangle, this small triangle, this small triangle, and so on. This small triangle should be the error. Okay. I hope things are a little bit clearer. And we also have MN, which is mid endpoint approximation. There, what we do is, by the name, you can like guess it. If this is fx, and this is a, that is b, and these are your x1, x2, and so on. Then for the each subinterval, smaller equal subintervals, it is considered the midpoint. So this point is in middle of a and x1, and you kind of consider the value of f at that point, and you form this triangle. The same for this one, the same for this one, and so on. So you can see you are kind of approximating the area under the curve by smaller pieces of rectangles. Okay, and the formula for mn is just delta x f of m1, where m1 is the middle point of the first subinterval, f of m2, and so on, say f of mn. Okay, let me just solve one problem, then I guess things will be a little bit more clearer. Okay, I'll just take one integration and try to apply all of the three different approximations we have studied so far to the same problem. Okay, so say it is asked to evaluate L5, R4, and say M3. So M3 is midpoint approximation, and this 3 says there should be 3 subintervals, so n is 3 in this case. R4, R means right endpoint approximation, and this 4 means there should be 4 equal subintervals. And kind of same logic goes for L5 as well. Okay, cool. So now my function fx is just 1 over x squared, right? Here. Okay, for L5, my n is 5, right? So remember delta x was b minus a over n, the general formula. In this case, delta x should be what? What is b? B is the rightmost endpoint, or the upper limit of the integration, which is 2. What is a? The lower limit, which is 1. And n here is 5. Okay, this is 1 over 5 or 0.2. So the formula for L5 should go like this. Delta x. So let me explicitly write the subintervals for you. So say the leftmost point should be 1 because the integration starts from 1. The second point should be 1.2, right? Because that is the small little nudge in x-axis. The next subinterval should be 1.2 to 1.4. The next one, 1.4 to 1.6, 1.6 to 1.8, 1.8 to 2. So there are 5 equal subintervals. Each of them are like length 0.2. So the formula goes like f of x1 plus, no, exactly the formula is. Okay, x1, x2, so on, plus f of x4. What is this? Delta x is 0.2. F of x1, what is x1? I'm using left endpoint. So this is my first point. So f of 1, this is the first point of the second subinterval. So f of 1.2 plus f of 1.4, similarly f of 1.6 and f of 1.8. That is it basically. And then if you just write it down more explicitly, it will be 1 over 1 square plus 1 over 1.2 square, 1 over 1.4 square, plus so on till 1 over 1.8 square. Let me just write it. Okay. Because remember, my function was 1 over x square. If you put x, it should give you back 1 over x square. Okay, good so far. And if you calculate this in calculator, you should get something like 0.58078, something like that. Okay, cool. The next problem was, say I denote this integration. Okay. The next problem was to find R4. Okay. So I was like 4 approximately. So here you can see my n is 4. My b and a are exactly similar. So delta x should be 2 minus 1 over 4, which is 0.25. Okay. So now my intervals looks like 1 to 1.25, 1.25 to 1.5, 1.5 to 1.75, and then 1.75 to 2. N is 4, so 4 equal subintervals there. Okay, cool. So if I apply R4, which is delta x plus f of x1 plus so on. It should be f of a anyway. Plus so on plus up to f of xn. Delta x is just 0.25 in this case. What is x1? I'm using right endpoint, so therefore this should be my x1 now, the rightmost point at the first subinterval. So f of 1.25 for the second interval, f of 1.5 plus f of 1.75 for the third, and for the last you have f of 2. Okay, cool. So we can simplify a little bit. 1.25 square plus 1 over 1.5 square, 1 over 1.75 square plus 1 over 2 square. Okay, so you need to put that in calculator. I don't have the answer right now. And you'll get the answer. Okay. For the midpoint rule, what you have to do is same kind of thing, but here I have n to be 3. So b minus a over n will be 2 minus 1 over 3, right? Which is 0.33. Now my interval becomes 1 to 1.0, sorry, 1.33, 1.33 to 1.66, and then 1.66 to 2. Okay. There is some error in this because, I mean, this should go till infinity, 0.3333 and so on. We don't want to work with that continued um, fraction in some sense. Therefore, we'll just approximate it like 0.33 there. If you want to be more precise, you just keep it as 1 over 3 and then work with that. That should also work. Okay, so if I put the formula for n3, right, it should be delta x times f of m1 plus f of m2 plus f of m3, where m1 is the middle point of this first subinterval, m2 is the same for second interval, and m3 is for the third. Okay. What is m1? M1 is basically 1 plus 1 over, sorry, 1 plus 1.33 over 2, right? That's how you find the middle point of two different points. You add them and you divide it by 2. For the second midpoint, I'll just add 1.33 and 1.66 and then divide by 2. For the third, I'll add 1.66 plus 2 over 2. Okay. And there is 0.33, the factor outside. Now, what is this? This is 0.33 f of, this will be 2.33 over 2, right? Plus f of 2.99 over 2 plus f of 3.66 over 2, which is just 0.33, and then f of 1.165 plus f of 1.495 plus f of 1.83, like this. And then this is just 0.33 times 1 over 1.165 square plus 1 over 1.495 square plus 1 over 1.83 square. Okay. And again, use calculator to have the exact value of this. So far we have learned 3 different ways to approximate the integration. Now we'll learn one more type of approximation, which is called trapezoidal rule. Okay. So I'll not go to the details of how we will get the formula because that will be a little bit cumbersome and maybe out of scope right now. So just one small remark is we use parabola to have the explicit formula for trapezoidal rule. But the formula for the rule is just delta x over 2. When you divide the main interval into n equal subintervals, then the formula should go like delta x over 2 f of x naught plus 2 times f of x1 plus 2 times f of x2 and so on. It will go till xn minus 1 and then just f of xn. Okay. And x1 is basically the first point. So let me just draw the graph real quick. To say you have this type of function, then basically from A to B, this is your x naught, x1, x2, and so on. This is your xn. Okay, cool. Let us quickly see an example. Say you are asked to approximate 0 to pi sine x dx. Okay. I mean, I know that this is not difficult to integrate. This is just minus cosine x and then from 0 to pi. But let's see if we use the trapezoidal rule, then is it a good approximation of the actual value or not? Say we want to use trapezoidal rule for n equal subintervals. So my n is 4. My delta x should be okay. My delta x should be pi minus 0 over 4, which is pi over 4. So my subinterval should start from 0, go till pi over 4, then pi over 4 to 2 pi over 4, then 2 pi over 4 to 3 pi over 4, and then the last 3 pi over 4 to pi. Okay, 4 equal subintervals. Now, if I use T4, it says I have half times delta x, right? Delta x over 2. Delta x is pi over 4. Okay, then f of x naught is the first point, 0. So f of 0, right? F of x1, which is second point. This is the second point, right? Pi over 4. F of pi over 4. Plus third point is f of 2 pi over 4 plus f of 3 pi over 4 plus n pi. Okay, so this is pi over 8 times sine 0 plus sine pi over 4 plus sine, this is pi over 2 plus sine 3 pi over 4 plus sine pi. So you can use your knowledge of trigonometry to say that sine 0 is 0. Sine pi over 4 is 1 over square root 2, I guess. Sine pi over 2 is 1. Sine 3 pi over 4 should be, okay, so starts from 0, then pi over 2, then pi. Okay, let me just draw the graph. It'll be a little bit easier. This is 0, this is pi over 2, this is pi, this is 3 pi over 2, and this is pi, 2 pi, sorry. So I know at 0, sine is 0, at pi by 4, it should be 1 over square root 2. At pi over 2, it is 1. And then at 3 pi over 4, it should have. Okay, so sine 3 pi over 4 will be again 1 over square root 2 plus sine pi is again 0. So basically this should be pi over 8 times 2 over square root 2, which is pi over 4 square root 2. And now if I just use our knowledge of integration, then sine x dx, right, from 0 to pi. Okay, this should be minus cosine x, I guess, from 0 to pi. So minus cosine pi minus cosine 0 plus cosine 0 actually. Because I have rather just write it into so minus cosine pi minus plus cosine 0. So for cosine pi, if I draw it, then it should go like this. This is 0, this is pi over 2, this is pi. So cosine pi is -1, so negative 1 plus cosine 0 is just 1, so this should be 2. Okay. And okay, so this is 2, but this is approximately, I guess, 0.55-ish something. So we can see that for this, at least for this example, trapezoidal root is not approximating quite good. But the thing is that when you increase this n to be, say, so this is for n to be 4. And if you use some coding or some software, and then you put n to be, say, 1 million, then you'll see that this the approximate value and exact value will be very small. That means like the error should be quite small. Okay, cool. Okay, so yeah, the next way to approximate uh, approximate the integration is called Simpson's rule. Okay, which is applicable when you take you divide in even number of smaller subintervals. Your n should be even. Okay. Oh, sorry, I made one mistake before. Trapezoidal rule uses trapezoid to have the explicit formula. For example, they kind of approximate like this. You just add these points like this. And then by that you will get a trapezoid, and you get this area of this trapezoid plus area of that trapezoid and so on. So this formula should not be very difficult to calculate if you use the formula for, area of trapezoid several times. Yeah, but to get the formula for Simpson's rule, you need to use parabola to approximate. And that might be a little bit tricky. So the formula is delta x over 3 f of x naught plus 4 f of x1 plus 2 f of x2 plus 4 f of x3. So therefore 4 and 2 will be like appearing one after another. Then 4 f of xn minus 1 plus the last is like f of xn. So you can see that f of x naught and f of xn kind of appears without any factor, but except that you will have 4, 2, 4, 2, one after another periodically. Okay. Examples. The best way to understand it will be to solve an example. Approximate 0 to pi sine x dx with S4. So kind of like same problem. So if I calculate delta x, it will be pi minus 0 over 4, right? So which is pi over 4. And then I'll get exactly this 4 sub intervals like the previous problem. Therefore, my S4 using the formula should be pi over 4 times 1 over 3, because I have this as my formula. Delta x over 3, and then f of x naught should be exactly same as sine 0 plus 4 sine pi over 4 plus 2 sine 3, pi over 2, 2 pi over 4 plus 4 sine 3 pi over 4 plus the last point is sine pi. Okay, which is pi over 12, and then we just calculate 4 times 1 over square root 2 plus 2 times 1, so 2, plus 4 times 1 over square root 2 plus 0. So it'll be pi over 12 times 8 root 2 plus 2, right? And if you put that in calculator, you should get 0.00354 and so on. So therefore, you can see that in this case, Simpson's rule is quite better, because the actual answer should be 2, exact answer, and it's quite close to that. Okay, cool. So far. Now one good question to ask at this point will be how good this approximation are. Okay. Okay, I realized one more mistake here. So you can see that I should multiply 2 there, right? The formula has 2, which I missed. That's why my approximation is so bad. Okay, so therefore I should have 2 there, 2 there, 2 there. So 2 over 2 plus 2, 2. Yeah, so let me just erase it. If you use calculator, it should be 1.896, something around that, I believe. Yeah, my bad. Okay, but still we can see that trapezoidal rule is kind of weak in this case rather than Simpson, because Simpson is getting like better approximation nearer to the actual exact value. Okay, let's come back. One good question to ask will be how good these approximations are. So say I is my integration fx dx. And then I'll just give the formula for calculating the measure of some error in some sense. So this is the maximum value of second derivative and then modulus of that between A and B. And say m star is the maximum value of f fourth derivative and like y2 slash fourth derivative of modulus of the function in the interval a to b. Then the formula to calculate the error, just call it as theorem, I minus Tn, where T is like trapezoidal, should be less or equal to m times b minus a to the third over 12n square. This is and for the midpoint rule, the formula is m times b minus a over to the 3 over 24 n square. This is for midpoint error calculation. And for the Simpson's rule, I should have m star b minus a to the 5 over 180 n to the 4 Simpson. Okay. Example, how this formula should be implemented. The next question. See, the question is how big my n should be to guarantee that you are, say, within 0.001 when you approximate the integration I, which is 0 to 1 e to the minus x square dx. Cool. See, I want to apply, I want to get the value of n for midpoint rule. Okay. So my fx is exactly e to the minus x square. F prime x is minus 2x e to the minus x square. And f double prime x is just 4x square minus 2 e to the minus x square. This is just product rule, using the product rule several times. You should check that I'm correct. And now if I use the formula for midpoint, then this should be less than equal to m times b minus a to the third 24 n square. But what is the m? See, my m was maximum value of f double prime of x, taking the modulus in a to b, in range a to b. So my second derivative is this. Okay. So basically I just plotted it in Desmos, a graphing software. And I have seen that it should be like this. Minus 2, so it's like this, and then like this. This is fx. And when I take modulus of fx, basically I should have something like this. This is plus 2, so and then, oh, sorry. This is my modulus of fx. And therefore I can see that m is 2 in this case. Cool. So if I apply the formula I minus mn, that should be less or equal to m, which is 2, times b minus a. B is 1, a is 0 to the third over 24 n squared. And this error should be less or equal to 0.001. And in this inequality, I have to basically solve for n. Okay, first simplify. So 2 over 24 n square is 1 over 12 n square, and that should be less or equal to 0.001. Just cross multiply. So I have 1 over 12 times 0.001 less or equal to n square. In other words, n square is bigger or equal to 1000 over 12. So n should be bigger or equal to square root of 1000 over 12. And that is basically kind of equal to what's the value? 9.128. Cool. So my n, which should be an number, like natural number, should be bigger or equal to 9.12. So what is the next natural number after 9.12? It's n. It's 10. So therefore, I can say that M10 will be with the range of 0.001 from the actual integration I. Cool. So let me solve this exact same problem for Simpson's rule. So the question is, what about Simpson's rule for the same problem? Then you need to calculate f4 time derivative of with respect to x. Then you'll get this. Again, you should verify this using the calculation. Using product rule. Okay. So the error should be the formula if I use. It is something like I minus Sn modulus less or equal to m star b minus a to the 5 over 180 n to the 4. Okay. Now what is m star? Remember m star was, try it again. M star was what? M star was maximum value of fourth derivative of f with respect to x. To take modulus of that, and you have to find the max in range a to b. So I see that fourth derivative of x is this. Again, if I use the graphing calculator, I'll get this as the graph of f. So this is like minus 5-ish. So modulus of f will be nothing but like this, and then this, right? Because the negative part will just flip and become positive. Exactly the mirror image with respect to x-axis. Anyway, so I can see that my m star should obviously be 12. Okay. So therefore, I minus Sn is less or equal to 12 times 1 minus 0 to the 5 over 180 n to the 4. And that error should be less or equal to 0.001. One remark is that there are other ways, like algebraic ways to find m star, but I guess you can use any graphing software and like guess what will be your m star and m in this case. Okay, so again, simplify. 12 over 180 n to the 4 is 0.1, and then cross multiply and multiply into the 4. So I'll have 12 over 180 times 0.001 less or equal to n to the 4. So n to the 4 is bigger or equal to 12,000 over 180. So n should be bigger or equal to 4th root of 12,000 over 180. Again, using calculator, that should be like 2.851 and so on. Now, one important remark is for Simpson's rule, n, which is the number of subintervals, should be even, right? And what is the even number after 2.85? It's 4, right? So therefore, my S4 will be in range of 0.001 from say I. Okay. So that was more or less about numerical integration. I hope you'll be able to understand at least some of it. And if you have any queries, questions, you are welcome to meet me in the office hours. Thank you.